For this lesson, we'll be focusing on waveguides. Waveguides are microwave transmission lines consisting of a hollow metal tube or pipe and use an antenna to launch an electronic and magnetic field through its waveguiding structure. And waveguides will sometimes mimic ductwork or any type of piping, and it commonly uses a microwave frequency range between 1 gigahertz range all the way up to 300 gigahertz range. So the big question is, why do we use waveguides? Why don't we use coax cable, antennas, or even fiber optics? Well, just like those methods, they all have their particular application. And it's always based on power, cost, and distance. Now I have an example here that was taken out of one of my books, and they actually have a 1 gigahertz signal being transmitted 30 miles. Well, if you look at the loss, it actually has the minimum amount of loss by using an antenna. And it's actually probably cheaper if you use an antenna method if you're trying to transmit something 30 miles. Now, if you take that same 1 gigahertz signal and want to transmit it 1,500 miles, it would probably be cheaper as well as less power usage or more efficient to use a waveguide. So it's usually based on your distance, your cost, and how much your power usage you would like to use. When designing your communication system using waveguides, it's best to be familiar with the two different modes, the transverse electrical mode and the transverse magnetic mode, TE and TM. The two different modes that exist are designed by two numeric subscripts, such as TE subscript 10 or TM 11. The first subscript defines the number of half-wave variations of the transverse field in the A dimension, that's usually the width. The second subscript defines the number of half-wave variations in the transverse field in the B dimension, it's usually your height. Now the most common mode you'll see is TE10 mode. The TE10 mode operation is known as the dominant mode. The dominant mode of any waveguide is the lowest cutoff frequency used for that waveguide. Now, as we mentioned in the first slide, waveguides are hollow tubes. Well, these hollow tubes can take on various forms. The four common forms we have is the rectangular form, cylinder form, rigid, and flexible. Now, the rectangular waveguide form is actually the most common due to the fact it's easy to design and easy to construct. The second type we have is the cylinder waveguide, and this usually mimics a pipe, and this is typically great for radar applications due to the fact it can rotate without impacting its performance. The third type we have is the rigid waveguide. This usually consists of any type of unique design due to the fact that in the facility you're using in, real estate is a premium, but it's usually more costly. The last type we have is the flexible waveguide. Now this one can bend and flex a little bit, but it's not typically used for permanent applications. They're great for temporary applications, or in this case, laboratories, or any type of application where versatility is required. Well, since rectangular waveguides are the most common, that's the one we're going to be focusing on for a lot of our calculations. But there's a few things we need to touch base on. One, anytime you have a lookup table with rectangular waveguides, you'll notice the height is always 1/2 of the width. In fact, if you look in the table at the bottom right, you're going to see the height is 1/2 the width almost 99% of the time. The walls are usually metallic, and it's typically filled with air as a medium. It's not always, but it's very common that it's usually air-filled. Also, when you think of waveguide structures, think of them as high-pass filters. So when you perform these calculations, you're looking for the cutoff frequency as if it was a high-pass filter. So any frequency below the cutoff frequency cannot be propagated. Now, what's very interesting about having waveguides with metallic walls, it makes it highly conductive for electrical waves. So anytime you transmit any communication down your waveguide, it's going to create a zigzag pattern, similar to fiber optics. Now with the zigzag pattern, there's going to be different angles, as well as two different wavelengths. There's going to be the guide wavelength, which is the distance from a point in time to another point in time of your negative z-axis, shown in the illustration there, and then your waveguide, which is the distance the wave travels in one cycle. And this is very similar to the transmission lines video. Now, we're not going to go too deep in the weeds on the different angles, but I want to actually provide you the equations, as well as we're just going to touch base on it so you know at least you're familiar with it. Now, as mentioned earlier, waveguides are typically filled with air or free space. Well, even air still has some degree of resistance. And this resistance is going to be your wave impedance. So we provided two equations below based on which mode you use for your characteristic impedance for your waveguide, the TE mode and the TM mode. Now, free space is typically 377 ohms, but I provide you the equation below. That way, in case they give you a different median, you can go ahead and perform your calculations using your permeability and your permittivity. So we can go over that a little bit more in the examples. Let's go ahead and jump in those now. All right, let's jump into our first example here. Right now we have to determine the cutoff frequency of the waveguide, and this is a WR62 for the dominant mode. The measurements shown are in inches. So right off the bat, we have just a simple rectangular waveguide, and it's in a dominant mode. As we looked over in the slides, the dominant mode is considered to be TE10. So right off the bat, we got the most popular mode, and it's going to be TE10. So this actually is going to make a lot of our calculations pretty easy. And the measurements shown are in inches. So the first thing we need to do is go ahead and take these measurements and convert them to the metric system. Now keep in mind, anytime you do these calculations, you want to do the internal dimensions of the waveguide. The thickness of the walls plays no part in these calculations. You're just looking for internal dimensions. So that means we're just going to take this number here and this number and convert it to the metric system. So I'll tell you what, I'll go ahead and do the width first. The width is considered to be A, which equals 0.622 inches. If you want to convert that to meters, you go ahead and multiply it times 0.0254. And that's pretty simple. That comes out to be an answer of A equals 0.0158 meters. And we're going to do the same thing for the height, which is considered to be B. So it's 0.311 times 0.0254. And that's going to give us an answer of 0.0079 meters. All right. So now we have A and B in meters. So that's already a great start. We want to find the cutoff frequency. We want to find that. Well, looking over here, I can find the cutoff frequency by finding the cutoff wavelength. To find the cutoff wavelength, I can use that equation right there, since it's in TE10 mode, or the dominant mode. So I'll just bring it down here. So it's going to be the cutoff wavelength is going to equal 2 times A. And since A is already in meters, we can go ahead and go 2 times 0.158 meters. And that's going to give us a cutoff wavelength of 0.0316 meters. Now that we have the cutoff wavelength, now we can go ahead and use this equation right here and find the cutoff frequency. So cutoff frequency equals, and this is going to be the speed of light over your cutoff wavelength. Speed of light is going to equal 3 times 10 to the 8 meters per second. That's going to be over your cutoff wavelength of 0.0316 meters. And that's a simple plug and chug your calculator. Let's see if I can fit it all in here. And without engineering notations, it's going to be 9,493,670,886. And if we change that to engineering notation, it's going to come out to be 9.494 times 10 to the 9 hertz, or in this case, 9.494 gigahertz. And that is your final answer. And that will be your cutoff frequency for a WR62 waveguide. So now we got our feet wet a little bit. Let's go into the next problem. All right, for our second example, we want to determine the cutoff frequency of the waveguide for a TM11 mode. The error dimensions are 72.1 millimeters by 34.0 millimeters with an air dielectric. So this one right here is a transverse 1-1 mode, and this one actually, based on the dimensions, mimics a WR284. And you can find this on a chart. Now this really doesn't matter which one it is, but just looking at the chart, I can actually look at it and say, all right, that's exactly the dimensions they gave me. But as long as they provide the dimensions, you're good to go. Well, same thing as last time. We want to find the cutoff frequency. We want to find that guy right there. Unfortunately, all we're given is, similar to the last problem, are the dimensions and the mode. Looking over here, I can find the cutoff frequency. However, I cannot use this guy right here because we have a different mode. We don't have a TE10 mode or a dominant mode. We have a TM11. So this one is out. So we're going to have to use this one right here. This particular equation you can use for any of them. The TE10 as well, but since TE10 is very popular, that's why this one was given separately, just because it's very common and very easy to use. But this one you can use for all of them as well. So first we need to find the cutoff wavelength. So we'll go ahead and use that equation. So I'll bring it over here, see if I can make enough room. And it's going to equal 1 over, and again, please excuse my handwriting. I know I say it in every video. So we need to know M, N, A, B. Well, this one's going to be M, this one's going to be N. So the first subscript is going to be M, the second is N, as in Mike, November. And just like we talked about before, this is the width, this is the height. This is going to be your width, this is going to be your height. And they're already labeled as A and B anyway. All right, so we're going to have a 1 over, because it's M, and then it's 2 times A, which in this case is going to be 72.1 times 10 to the negative 3. And I'll see if I can clear my handwriting on the next one, and that's square, plus, we're going to do the same thing again, so it's parentheses, and it's going to be 1 again, because November is 1, over, and it's going to be 2 times, and this one's going to be the height, which is going to be 34.0 times 10 to the negative 3 meters, because that's in millimeters, so it's always going to be 10 to the negative 3. And let's see if I can close parentheses, and then square that one. All right, so I know it's ugly, but we'll work through it and it'll look a little cleaner. We'll go ahead and solve these denominator right here first before we do the square root. So we'll go ahead and say 1 over 2 times 72.1 times 10 to the negative 3. So that way we can just go ahead and see if we can clean this up. So it's 1 over, I want to rewrite the whole equation, square root, and then we have, we'll go ahead and solve this part in the calculator, which is going to be 6.935, and I'm going to round for a majority of these, plus, and do the same thing again over here, which is going to be 14.706 square. Now we can go ahead and square both of these, so it's going to be wavelength cutoff, 1 over, square root again. This one's going to be 48.09 plus 216.27. And that's pretty easy plug and chug. I'll tell you what, let's see if I can bring it over here real quick. So it's 1 over square root, and this is going to be 264.36, and that's going to equal 1 over 16.26. And this is still in meters. And that's pretty simple plug and chug, and let's see if I can fit the rest right here. So my wavelength cutoff is going to equal 0.0615 meters. So I want to go ahead and clean this up right here and get rid of all this so I can finish off the frequency cutoff now that we have the wavelength cutoff. All right, for our frequency cutoff, same thing as last time. We're going to use this equation right here. So it's going to be speed of light over your cutoff wavelength, and that's 3 times 10 to the 8 meters per second over, and then we have our cutoff wavelength, which is 0.0615 meters, and that's a simple plug and chug. So it's 4,878,048,780 hertz. And we'll see if we can make an engineering notation. So it's going to be 4.878 gigahertz. And that is your cutoff frequency for this waveguide. Let's jump into our next example. All right, for our last example, we saved the best for last. We're going to determine the wave impedance for a Tango Echo 20 mode that's transverse electric 20 mode with a air dielectric of a WR62 waveguide and an operating frequency of 20 gigahertz. Well, this WR62 waveguide is the same one we had from the previous example.
So we might be able to use some of the variables from that one. So what we want to find out is Z of O. That's the one we want to find out. Now, the thing to keep in mind is when you look at the equations we have for Z of O, you want to keep in mind which mode you're using. Since we have Tango Echo, this is the equation we're going to be using. We're not going to be using the transverse magnetic one because that's not the mode we're using. So just keep that in mind of which mode you're in for which equation. All right, for this example, we're probably going to have to write down our knowns and unknowns just because there's a little bit we're going to have to go through. All right, so this is what our unknown is. Now let's write down our knowns. We know A and B from the previous example. A and B is going to be 0.0158 meters. B is going to be 0.0079 meters. All right, so far so good. We know our operating frequency is 20 gigahertz, so that means F is going to equal 20 gigahertz. All right, and we know M and N, Mike and November, so we know that one's Mike and that one's November. So the first thing we're going to want to find is the wavelength and the wavelength cutoff. Well, I'm going to do the hardest one first. Let's do the wavelength cutoff. So it's going to be this equation right here due to the fact our mode is not the dominant mode, so we can't use this guy. Well, this one's actually going to be quick and easy. You'll see. So we're going to do the wavelength cutoff equals 1 over the square root of M, which is 2, over 2 times A. So it's 2 times, and alpha is, I'll say times, 0.0158 meters. Now here's the great part. It's going to be plus N over 2B. Well, since N is 0, it's going to be 0 over 2B. So it doesn't matter what those numbers are in the denominator. This automatically is going to become 0. So it doesn't matter. And then, of course, we're going to square both of those. So let me go ahead and close these brackets and square it. Square of 0 is 0. So this is going to clean up really quick. So let's rewrite it. Wavelength cutoff equals 1 over the square root of 2 over 2 times 0.0158 meters. And that's going to be square. Rewrite it again. If you plug and chug this in a calculator, it's going to give you an answer of 1 over the square root. And we're going to go ahead and say 2 over 2 times 0.0158 is going to give us 0.0316, close parentheses square. And I might be able to do this one more time right over here. 1 over square root. And this is where we're going to have 2 over 0.0316. And that's going to give us 63.291 square. Well, the real good part about this is, anytime you have a square and a square root, those two are going to cancel out. So you're actually just going to have 1 over 63.291. So in other words, I could probably fit it up here. Wavelength cutoff equals 1 over 63.291. And that's an easy plug and chug in your calculator. It's going to give you an answer of 0.0158 meters. It's funny, it's the same thing as our alpha. All right, let's put our knowns over here. All right, let me clean this up for our next part. So I saved the next one as the easiest one. So we're going to look for our wavelength, which is going to be wavelength equals, we'll use this equation right here, C, in other words, your speed of light over your frequency, which is going to be your wavelength equals 3 times 10 to the 8 meters per second over your frequency, which we have right here, which is 20 gigahertz. And that's a very easy plug and chug. It's going to give us an answer of 0.015 meters. And I'll make sure I put my units here as well. So we'll bring this over here. Now right here, like I said in the PowerPoint, your air dielectric is going to be 377 ohms. So that means this guy right here is going to be 377 ohms. All right, so I'll clean this up and we'll keep moving forward. So I'll rewrite our equation. It's going to be air free space impedance, and that's going to be the square root of 1 minus the wavelength over the wavelength cutoff, and then close parentheses and then square those. So rewrite again, but we'll go ahead and fill in our variables. So 377 ohms over the square root of 1 minus, and then we have our wavelength, which is 0.015 meters over, and it's going to be 0.0158 meters, close parentheses, and then square. So we'll go ahead and do 0.015 over 0.0158. See if I can rewrite this again. 377 ohms over the square root of 1 minus 0.949 square. And I think we can fit one more down here. 377 ohms over the square root of 1 minus 0.909. And that's an easy plug and chug in our calculator. It's going to give us 377 ohms again over the square root, and I'll round, 0.099. So little by little, I'm just working this down, that way you can see my math. And the square root of 0.099 is going to give us an answer of 0.315. And last but not least, our final answer, which is going to be 1,196.83 ohms. So that is going to be our wave impedance for this waveguide. All right, this wasn't too hard. Hopefully this is enough information to get your feet wet and get familiarized with the equations. Now, I didn't get too deep in the weeds when using our angle equations here as far as the zigzag pattern down the waveguide, but I want you to just be familiarized that they're there, and you can use them as you need. If you have any questions, feel free to let me know, and I hope you all have a good day.